In this example, let's consider a beam, and let's concentrate on a cross-section that's indicated with the red cross-section mark. And let's assume that the beam has a rectangular cross-section, b by h, and the coordinate system is placed right at the center of the cross-section. And we'll use the usual axes of x, y, and z. And also given is that the bending strains, sigma xx, are linear on the cross-section with respect to y, so minus beta times y, beta is a parameter given, and that the shear stresses are parabolic on the cross-section. So sigma xy is equal to alpha h over 2 squared minus y squared. So alpha is also a given parameter. And so this is a shear stress distribution that's 0 on the top and the bottom of the beam, and it takes its maximum value at the center line of the beam. And let's go ahead and try and determine what the resultant forces on this cross-section, V, R, and M, are for this type of stress distribution. So to do that, we'll use our general relationships. First, we'll start with the internal force R, so the axial force in the x direction. So it's an integral over the cross-section of the beam, so that's a double integral. So minus b over 2 to b over 2 in the z direction, and from minus h over 2 to h over 2 in the y direction. And we integrate sigma xx to give us that resultant force. So if I plug in sigma xx, so that's minus beta y, so when I integrate y, I get y squared over 2, and I evaluate at the limits, minus h over 2 to h over 2, and if I do that, I'm simply going to get 0 in this case. So the resultant force R for this stress distribution, which is a common stress distribution, is actually 0. Now the shear force is again the integral over the area of sigma xy. Again, it's a double integral with respect to y and z, from minus b over 2 to b over 2 and minus h over 2 to h over 2. I can plug in for sigma xy, so I plug in alpha h over 2 squared minus y squared, and if I integrate that and evaluate at the limits, I find I get b alpha h cubed over 6. So it's just simply, it's a very straightforward process if you know what the stresses are to determine the internal forces. You just do it by integration. The moment expression is the integral over the cross-section of minus y sigma xx integrated with respect to y and z, and again I just plug in the expression for sigma xx, which is minus beta y, and perform the integral, and I get b beta h cubed over 12. So that gives me the expressions for the three resultants. There's the bending moment, there's the shear, and there's the axial force. So 0, b alpha h cubed over 6, and b beta h cubed over 12. Just to sketch in that stress distribution in the system, I've plotted here on the cross-section sigma xx in red, so it's a linear variation, and the shear stress distribution is parabolic, and that's sigma xy. So it's 0 at the top and the bottom, and it takes on a maximum value at the center there. And what we've shown here with this calculation is that this set of stresses is equivalent to a bending moment of the given value and the shear force of the given value. So these are in a way statically equivalent descriptions of the same state of stress in the system.